This is video 33 on MicroPython and LVGL 9 on a Raspberry Pi Pico. We searched the internet for an interesting LVGL MicroPython example that can help us learn new concepts. The demonstration is running. The LVGL MicroPython program on an ESP32 chip was written by a talented programmer in Germany. The display shows the simulated capture of DHT temp and humidity data, normally updated hourly, though for this demo it updates once a minute. Please let us know in the comments if you like this example, or let us know if you have suggestions to improve it. For this effort, the rig is using a Pico W board inserted into a Pico MicroPython display baseboard. The author used an ILI 9341 display, so our project does as well. As this channel covers multiple small system solutions over time, please subscribe to stay informed and click like, as that really helps. Early on, I had several goals in mind for this effort. I hoped to find an example that uses the Pico W's networking features. Secondly, I wanted some interesting LVGL graphic features. And finally, I wanted to be able to use more MicroPython features in general. In the next 3 slides, we will discuss the new concepts. Finally, we will review the code. A program author called FabCHack has an LVGL 9 MicroPython program I felt that met most of my goals. I like it because, firstly, his program uses the network. It connects to the NTP time server and publishes data values to a remote MQTT server. Secondly, the program has interesting LVGL graphics. For example, he sets a dark theme for the screen, which seamlessly sets up color on the other LVGL objects. Also, I thought he was clever on how he squeezed the charts and data into such a small screen. Thirdly, the program uses interesting MicroPython features, such as the Asyncio module to implement data and LVGL updates as async task. Also, he used the NTP time and DHT functions, which are intrinsic MicroPython functions in the Pico W firmware. And his GitHub site is mentioned in my acknowledgments. By the way, his GitHub site also contains the STL files to 3D print a case for the display and board. Let's talk about MicroPython networking. This slide from the MicroPython documentation explains Wi-Fi connections can be either station interface or access point interface. The doc explains that one uses station interface to connect the Pico to their router's internet, and thus the Pico gets a random router-based IP address. One uses access point interface instead, which assigns 192.168.4.1 to the Pico, so that another device, like your desktop or phone, can connect wirelessly to the Pico. The author wanted the station interface so that the code could connect to the NTP time server, and also to update a remote MQTT server. For our program, I kept the NTP connection, but I disabled the MQTT publish function. I wanted to defer MQTT to a future video. If you're interested, though, the code is there in the file, but as comments. The MicroPython doc explains that there are several async functions. First, you declare an async task by adding the word async in front of any callback function. Next, you declare a main function to register the async task by using the createTask function. Finally, the bottom of the code performs an async.run on the main function. This is the endless loop. Notice that the async task does some setup code and then performs an await async sleep. In this way, the MicroPython Asyncio scheduler executes the next task. In the program, I noticed that the author used the NTP time and the DHT functions from the MicroPython firmware. The program returns from the NTP time server and performs the NTP time function to set the Pico W's current date time. The program uses DHT11 connected to a single pin, but I replaced the code with a simple simulator. In our case, I replaced all the DHT11 features with my own. And I did this in case you do not have a DHT11 or DHT22. In our demo program, you are seeing just the simulated values. Let's discuss the program code running the demonstration. It turns out that the Pico W with the April firmware fails any network connection time. So we are using the February 2025 firmware on the Pico W. We are using all of the same driver files from Video 32, but please update the new file secret.py with your wireless SSID name and password. Now let's walk through the code. The code begins with the imports, and what's important here is I've commented out all the imports that the author used that he had available on his ESP32 firmware and replaced the imports that we need for our Pico. So for example, on the ESP32 it uses something called LCD bus and the ILI9341 driver, but I replaced that with our display driver. Otherwise, I use the functions as he implemented. Notice that I added the import for random, and this is so that we can do the simulated values, as you'll see later. Okay, now we come to the code where I extract the secret SSID name and password from your file, secret.py. So if you're missing the file, you could just update lines 33 and 34 instead. The connection to the wireless is a bit temperamental. And so this value for the number of retries before it will fail. If it fails, then instead of using the current date time, it's just going to use a value starting at 5 a.m. Next, I define a function called reset button using pin 22. And this is a hardware button on my baseboard that I've connected and configured that you'll see later to perform a hard reset of the board because the display has no buttons and no way to exit out of the program. Next, because I was concerned about memory, I have a couple of garbage collection functions that collect and return the memory free. Here's the code I normally use for the black screen and with a border, and I replaced that with the author's use of a dark theme. And we know it's a dark theme because if we look up theme default init, the third parameter here is what's used to set the screen to either dark or white or light. Next, we have a huge section on the UI commands. And there's not much to be said here other than walking through these. We have a section of code to set up the temperature chart wizard axis and the y-axis. And here we've set the color of the series data. Now he uses the color hex. And so this is essentially, if you think of these first two as red, green, blue, this is essentially giving us a green color. Next he sets up the humidity chart with widgets. So you have chart itself, you have the chart's x-axis, and he fully defines all the parts, which I thought was interesting, and the y-axis. And then he sets the color for the data series, and here you see we're using FFF, which turns out to be a combination of red and green, which produces the color yellow on our screen. So that's how the humidity becomes yellow. So it's just a different way of doing colors. He turned the scroll bar off on these charts because he didn't want the screen to move. So he's not using any touch features at all. And in case you did, we do much of the same thing for humidity. Oh, we do much of the same thing to set up the other values on the screen. So here we're setting up the label temperature and its data. We're setting up the label humidity and its value. Commands for all of the information labels and information data fields that's at the very top of the display. So here you have the time, the Wi-Fi, the statuses, another label and its status, the IP and its data value. And then he sets up these punk objects, which are very small objects that are at the top of the display in colors, and I'll come back to them later and they'll make more sense. Next, he sets up something that I thought was interesting. For the frame status and temperature, he sets up these colors, but then gives them a very small opacity value. So normally you would have 100 here, so you would get a bright color. So if this was, say, yellow, you would see bright yellow. But because this number is so low, you get this very faint grayish color on the screen, and it nicely contrasts with the black screen. So you get these nice framed outlines and background for the chart and on the display. And I just thought it was interesting how he did that. At line 300, we have the typical command we use on the Pico to load the screen, which is not needed on the ESP. So I added this command. And then I do another garbage collection. So now we're getting into the bulk of the code. First, he sets up the Wi-Fi manager. And this is to connect to the Wi-Fi, as you'll see here. And when I was doing this, I was researching ways to make this more reliable. I left in the comments here in the code a discussion on the internet about making the network connection more reliable. In the end, I improved it a little bit by putting in this counter and a number of retries and then a delay, which he did not have in his code. But after so many tries, it's going to then raise this error, which does not kill the program, but just breaks out of this infinite loop that we're in right here, that we would just remain in forever, and our code wouldn't ever work. So I thought that was an interesting way to handle that situation. We would not get the current date and local time, but the Pico would then use its default local time of 5 a.m. and proceed from there. Then there's a bunch of code here that would display the connection information to the screen. I've replaced that with the command connect it with secret SSID so that nobody would see somebody else's actual wireless device. Okay, so we're currently going to stop the program and restart it because I just noticed that the network had failed to connect. So we're going to try it again and see if it connects. Okay, as you can see, it's connected, and our screen now has a proper IP address and the proper date time. Now, I left in this code for create access point. There's no provision for how to use a connection to the Pico as an access point. But I left this code in just so you have an example of how to create an access point. All right, now we come to the part of the code which is German time. Now the author is from Germany, so he has set up code to get the current date time from the local German NTP server. And that was an initial cause for some of my connection issues. So I replaced his Germany pool NTP host name with the one that I have in the US. So you could replace this with the NTP server name for your region instead. Once I do that, it then sets the date time in the Pico, as you can see in the code. He uses all these German words right here, and so stell sieht ein is translates to set the time. And we can see this as the actual time. So here, he's taking the UTC time that he gets from the utime function, and he's converting it to local time by using the proper UTC offset. In his case, in Germany, he's +1. But here on the east coast of the US, I'm -5. So I've updated the offset to -5 in my code, and that's why I get the proper time. 1030 is indeed what it is here in the US. Then on line 393, he's getting values for year, month, day, hour, minute, and second. The capture of this information is important because we're going to use the hour in a few minutes as part of our x-axis. Now, the last thing he does is he checks to see if it's summertime, and he updates the current hour with the proper time for summertime. This isn't quite the formula that we use in the US, but I just left the code as is because it doesn't hurt. All right, as I mentioned, one of the things this function does is it asynchronously updates the time on the x-axis with the current hour, because he captures data hourly. Well, that's great for displays sitting next to your bed, but in our case, I'm running a demo, so I changed the timing scheduler to once a minute. And so instead of displaying the hour value on our x-axis, I'm displaying the current minute value on our x-axis. And you'll see that in a few minutes when it finally updates the 10th value. So how does it do that? Well, he takes an hour list of 10 values, or in this case 8 values, and he appends the current value on the right, and then pops off the earliest value, and that's his list. And you'll see he uses that approach for his temperature and humidity list as well. So he prints all that off to the shell, so we have values in the shell and we can see what's going on. Now we come to one of the first tasks, and that's this task called tick. So he's using this as a way to update the LVGL functions once every period. And so he needs to include task handler for ESP32, but for the Pico we use timer handler. Now we come to the asynchronous task to update the temperature and the humidity values. So as you see here, we're capturing the data using the D routine. So D, as you'll see a little bit later, is the stands for DHT. And I'm using D to be the simulated class of data. So I'm getting a simulated temperature and a simulated humidity returned by these functions. But if you use the actual DHT device, you would get the generated DHT value from that device. Failing all that, you could just hard code in temperature and humidity so that your display gets you some values. Again, like he did with the hour list, he has a list of 10 values that he updates by inserting the latest temperature on the far right of the list, and he pops off the earliest value on the left. So he maintains a constant list of 10 values. So this array, temp list and humidity list, will be used later by the LVGL chart function to display data on our charts. Next we have the asynchronous task to update every hour, but if you recall, we're going to actually update every minute. And when we do, each update occurs by awaiting an update from the above functions, and when it finishes, it comes back and prints off a temperature and humidity current list. Then it goes through the chart, and here is where that external array for the data series temperature chart is updated, and the y-axis range is updated, and he sets the range of the y-axis. So if you were watching the screen, when it updates, you'll see that the y-axis values are changing once a minute to the current low and high range, and the x-axis are changing once a minute to update with the current minute. So 32 on our x-axis represents the data at minute 32. And it does a similar thing for the humidity chart. Finally, beginning at lines 518, you'll see where he's updating the values of the temperature and humidity, which is those values at the far left middle of the screen that have the last temperature and the last humidity. And again, I'm using values from my simulator instead of actual values. And I did this particular change right here because you'll notice that it's going off and getting another random value from the DHT device. So that value could be different from what's actually on the display. And so I changed this code slightly to use the last temperature and the last humidity value instead of capturing a new value and displaying that, which is completely different from what was in the chart or what's in our list. Next, we have code for the MQT publisher. So this would connect to a remote publisher and update a topic with the current data values. In the next couple lines, and remember, we're updating these every time we do a measurement. Okay, so on his application, he had defined neopixels as sort of remote indicators on his display. And so he changes the lights based on what it's doing. Well, I didn't want to use neopixels if you didn't have it. So what I did is on my baseboard, I configured 3 LEDs to represent the same actions as his neopixels. In his code, he runs a function to set those LEDs on the neopixels. And so my code is doing something similar with the LEDs. So it sets a particular LED color on. In this case, it's usually green. It goes to sleep for 30 seconds. Then it sets the red LED and goes to sleep for 30 seconds. So once a minute, you're going to see the green and red flash, which lets you know when a measurement occurred. Gives you some visual feedback that something's happening on your application. Okay, I promised I would explain the punk. And here, this is going to make some sense. So the punk is, again, those dots at the very top of the screen. And if you've been watching the screen, you notice that they're changing color once a second. And this is the task that does that. So this task runs once a second. And we see that because it's awaiting a sleep of 1 second. And it sets the color of punks 1, 2, 3, 4 to this pattern of colors. And then another second goes by and it sets it to a different pattern of colors. Again, it's just a way to give the user some visual feedback that something's happening on the MicroPython chip. Next, we have the task to do the reset. So as you recall earlier, I defined a button, pin 22, as my reset button. And here I'm capturing the press of the hardware press of that button, which would be 0 if it's pressed. And so if the button is pressed, it will do a hard reset of the microcontroller and break out of all this. All right, we're coming closer to the end now. So if you recall, I have all these asynchronous tasks. So for example, the do reset is defined as task 0 right here. So here I'm registering all the asynchronous tasks that we discussed above. The do reset, the task to do things once an hour, or in our case once a minute, the task to do something once a second. We have the task to do the my time tick. And then these are all awaited in this asynchronous gather function. So this function creates the task list, and essentially our scheduler. Finally, we come to 2 classes that I created to simulate the NeoPixels first and the DHT. The first one is to simulate the NeoPixels. So I created this LED class, and I defined the default LED, which is known as GP25, on my Pico as LED 0. I defined pin 26 as LED 1, and I defined pin 27 as LED 2. When I first initialized this LED class, which is at the start of the program, I turn them on and off. And so essentially all the lights of the baseboard will light up at the beginning of this program. Thereafter, I perform the turn off function and the fill function and the write function. So in his code, he is doing a fill or a write and of the NeoPixels. And so I created this fill function to simulate his NeoPixel fill function, and I created this write function to simulate the NeoPixel write function. Since the fill is accomplishing everything we want in turning on an LED, I just set the write function as pass. But I left these in so that we could use his code unaltered as much as possible. In a similar vein, I created a simulator for the DHT. So I initialized DHT with the last temp and humidity values. Then I configured a measure a temperature. So just like the DHT has a measure function if it is actually running, I have a measure function in our simulated DHT class. I then have a simulated temperature function and a simulated humidity function. The temperature function just takes 22 plus some random integer between -5 and 10. So that actually means that we will get temperature values between 17 and 32 degrees Celsius. Also, for the humidity, have a starting value of 30. So that means we'll get starting values, we'll be getting humidity values between 25 and 45 on our chart. And that's because I live in a humid part of the world. So if you live in a drier world, you could just change this starting value and change this range appropriately. Now we come to the main part of the program. First, you see the code he had for NeoPixel. I just commented it out and replaced it with my LED code. He then initializes all the UI text at the start of the screen, at the top of the display, and waits a second. He then initializes the DHT and gets an initial value for the temperature and humidity. He prints off the initial temperature and humidity values, and then he proceeds to the Wi-Fi manager to get a connection using the secret SSID and the secret password, or the access point. Now, I didn't want my actual wireless SSID device name to be displayed in this video, so I replaced the value that the Wi-Fi manager returns with the word secret. So when we look at the display, that's what we would see in any output. Again, we have some more fields here to set the statuses of the information fields at the top of the screen. So it's going to hard code the MQTT status. It's disabled because we physically disabled that, but it will return the actual proper status from the actual Wi-Fi connection, and it will return the actual IP address. So the IP address that you're seeing on the screen is from my actual wireless device router. I then test the LED values by turning on the LED on the USB device itself. I collect 10 initial temperatures and humidity values that I populate the chart with, and then I fall to the very last command, which is the asynchronous run command that performs the endless loop on that main task function. And we'll look at the values for a second, and you can see it's got the current temperature and humidity values on minute 47, 48, 50, 52, 54, and so on. Okay, in summary, in this video we presented the temperature humidity example LVGL MicroPython program. We briefly discussed networking and asyncio. We demonstrated the program. We reviewed the program. Now you have an LVGL 9 MicroPython example. Although the original code was written for ESP32 LVGL MicroPython, I simply replaced his display bus definitions with our display driver interface. And the remaining code pretty much worked as is. I did make a few tweaks, so please comment if you feel any other changes are needed. I hope this video helps your LVGL MicroPython coding. Thank you for listening.